Okay, homework over infinite series. This just said give me the first 5 terms and use the nth term test to determine whether it diverges or could converge. So the first 5 terms, this is how I wrote them in the answer key. The first 5 terms, if we were writing it out the long way, would be 1, 3, 6, 10, 15. Like individually add them together, but there's the first term together that would make the second sum, the third sum, the fourth sum, the fifth sum, and so on. So write out the terms, but then tell me if it diverges or could converge. So what is the limit as n approaches infinity of this function? Well, it would be infinity, not 0, diverges. Problem number 2, you can see the individual terms. The limit as n approaches infinity for these terms is 0, so this could converge. Number 3, this one is a little bit tricky. The limit as n approaches infinity, it's natural log infinity over infinity, which are both infinitely large, but so that would be infinity over infinity. So this one needed L'Hopital's rule. Derivative of natural log n is 1 over n. Derivative of n is 1. So that would be the limit of 1 over n, which is 0. So this one could converge. Number 4, here are your first 5 terms. And here's the sequence. So when I find the limit of the individual terms, that would be n over n squared plus 4 square root of n squared plus 4. If you simplify that, you would get, like the square root of n squared is just n. So isn't this kind of n over n? Yeah, it kind of is. But you could also do L'Hopital's rule on this one, because that would be infinity over infinity. And then that would be the limit as n approaches infinity of 1 over 1/2 times n squared plus 4 to the negative 1/2. So the negative there would flip all of that. So divided by 1/2 is the same as times 2. And if we flip that, it has a negative exponent, so it would flip to the top. So that's really the same as 2 times square root of n squared plus 4 over 1. And that would be infinite, definitely not 0. So that one definitely diverges. On this one, another L'Hopital's rule, you could see, trying to decide how much time to spend going over this one. The limit of 2 to the n would be n natural log, 2 to the n natural log 2. The derivative of n factorial would be a really big number. And then if we plugged in infinity, these are both going to, I'm not going to spend more time on it because I'm kind of stumbling over my words right now, trying to explain it. I need to look up what the limit of n factorial is. I guess the best way to explain it right now is 2 to the n is getting bigger. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. But n factorial is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. And then you can tell that they're both increasing, but this one is increasing way, way, way faster. So if the bottom number is getting way, way bigger than the top number is, you're dividing by a number that's way larger than the bottom. You're dividing by an infinitely big number, then that's going to approach 0. And I don't know if I explained that really well, but if we need to go over it in class, somebody just let me know and I'll be happy to talk about it. This last one. So here are the 5 terms, and the limit as n approaches infinity, this one oscillates. So up, it goes up and then down and up and then down. So the limit doesn't exist, so this one diverges. What about these? So on these, you had to write the rule yourself. They've all got a square. So what do they have in common? They've all got a square root. Okay, so that's going to be part of my formula. 3 times 3 is 6 times 3 is 9. So this is 3 times 3, 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. So the bottom is 3 times n. The top number, those are all odds. So one pattern that you should probably be familiar with is the list of odd numbers is 2n minus 1. So if I multiply by 2, I get evens, and if I add 1 to it or subtract 1 from it, then I get a list of odds. So here's my nth term, and the limit as n approaches infinity, it would be square root of 2 over 3, which is not 0. So that series will diverge. The sequence converges. It gets infinitely closer to a square root of 2/3. But the sum of the terms does not get closer and closer to some specific value. So the sum diverges. Individual terms converge to root 2 over 3, but when I'm adding them up, there is no limit. Number 8, the top number is the one that stood out to me the most. Term 1, 2, 3, 4, 5 had 1, 2, 3, 4, 5 on top. And on bottom, those were all powers of 2. 2, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So there's that. And the limit, this is another one where, it's technically a L'Hopital's rule. That would be infinity over infinity. Derivative of n, derivative of 2 to the n. So then you can see that that would approach 0. So because the limit of the individual terms is 0, the limit of this series, what they all add up to, could converge, could have a limit. We don't know for sure, but it could. Number 9, this pattern was weird, but I don't think hopefully it wasn't super hard to figure out. We've got a 2, 3, 4, and 5 in front. We've got a 2, 3, 4, and 5 root, and the root is always root of e. So this one, you're multiplying by a number that's getting smaller and smaller, but you're multiplying it by a number that gets infinitely larger. So that's not 0, so that will definitely diverge. If you needed to work this one out further, then you could say that this is n times e to the 1 over n. And you could do the product rule and then plug in infinity and do a little bit more algebra if you needed to convince yourself that the limit is not 0 and that will diverge. The telescoping ones. So I started by plugging in 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7. And I needed quite a few of these. I didn't do this just for y'all. I did this because I needed quite a few to see what's going to cancel out and what's not. So when I looked at what did not cancel out, what was left, the 3, the plus 3 halves, the plus 3 over 3 were left. And then if we kept going on and on, we would have whatever we plugged in last. And so that is your S sub n. That is your formula for the sum. So what is the limit of that sum as n approaches infinity? Well, as n approaches infinity, these terms are still going to be there. These are not, and that adds up to 5.5. So the sum of that sequence, you could add those terms up forever, and they would get closer and closer and closer, infinitely closer to 5.5. On this one is like the last example in the notes where you had to do partial fractions. There are a couple of different patterns you could have noticed for the bottom here. These are all one less than a perfect square. So perfect squares are 4, 9, 16, 25, 36. These are one less than that. So the pattern that I used was n squared minus 1. And that factors to n plus 1 and n minus 1. So I'm going to rewrite this using partial fractions. To figure out what goes on top of the n plus 1, well, what would make n plus 1 equal 0? Negative 1 would. And if I plug in negative 1, I get negative a half. What goes on top of the n minus 1? Well, what makes n minus 1 equal 0? 1 does. And if I plug 1 in, I get 1/2. So I'm going to switch up the order so that the subtraction sign is at the end. But you can see, hopefully, that that's this. You also, if you wanted to, could rewrite that as 1 over 2 times n minus 1 minus 1 over 2 times n plus 1. You could distribute the 2's if you wanted to and make it 2n minus 2 and 2n plus 2. You could write that several different ways. So then when you start plugging in your terms, plugging in your numbers, I plugged in 1, plugged in 2, plugged in 3, plugged in 4. And I could see from that the 1/2 was not ever going to cancel out. The first term that canceled out had a 6 on bottom. And everything that had a 6 or bigger on bottom canceled out. The 6 canceled out. The 8 canceled out. So the 10 is going to eventually cancel out. So is the 12 and on and on. But that 2 and 4, they're there. There isn't going to be another term that has 1/2 or 1/4. So that tells me that those two are going to be left. So my S sub n, I would have the 1/2 plus the 1/4 plus whatever terms were left at the end. But when I do the limit as n approaches infinity of that, then the ones with the n are going to go away, and the sum is 3/4. So if we could add these terms together for infinity, then they would add up to 0.75 to 3/4. I know that maybe it's not a problem for y'all. The idea of an infinite sum sometimes makes my head hurt. So I can't add these up together forever. So if I can't add something up forever, then how can I find out what it would add up to if I could? I get that that's hard. Or maybe it's not for y'all. I hope it's not. It is sometimes for me. But it's kind of like the idea of asymptotes. When you were in, well, I don't know, whatever grade y'all started talking about asymptotes, it was the same problem for a lot of people. So you're telling me that this function is going to get forever and ever and ever closer to 0, and it's never going to cross it? It's never going to cross that line? It's the same idea, just a different application, a more advanced application. But yeah, there's some number it can get infinitely closer to and never cross. That's the same idea as an infinite series. So if that's not something you struggle with, great. If it is, then maybe you can do what I do and just say, okay, on one hand, I know it kind of makes sense. On the other hand, it kind of doesn't make sense. And then you just apply the rules and trust the process. So I hope this helped you guys. And if you have any questions, let me know.